folks, welcome to the processing lab. Today we're going to go over how to use the curve tracer and IV machine. So if we step out of the entryway and we walk towards these machines, we'll demonstrate a couple of their uses. Alright, so going from left to right, we have the curve tracer machine. We have the microscope and probe setup. These are connected to a toggle box, and in turn those are separately connected to the CV machine, to the IV machine, and the computer with LabVIEW that we use to analyze them. Now, first things first, what we're going to go over is how to actually load a sample. Number two, we're going to go over how to use the curve tracer. And then number three, finally, we're going to go over how to take IV measurements using the computer.
So first, we're going to load our sample. To do that, go to your optical microscope. And underneath it, there is a base plate that is conducting, and two probes that you will actually be using, and a third probe that you could theoretically use for 3-terminal devices. So to start out, take your tweezers and your sample and load it onto the base plate. Now you will turn on your optical microscope. This light level is adequate from experience, and looking through your optical microscope, you can adjust your probe level to place your probes on the correct terminals of your devices. To move the probes, use the 3 toggles. This toggle moves the probe in this plane. This toggle moves the probe in this plane. And this toggle moves the probe up and down. Let's take a look through the microscope. As you can see here, these are our 2 probes. The rightmost one is controlled to be placed onto the silicon dioxide. The leftmost probe is placed onto the aluminum contact. Since there's doped silicon underneath the aluminum contact and the silicon dioxide, we would expect a MOS capacitor.
Alright, so let's go ahead and take a look at how this thing is connected up electronically, right? So, going from where Vince left off here, we have our A and our B probes. Now, I know it's kind of hard to see through the convoluted tangle of wires, but the ground plane is connected by a thin wire to the ground port of the microscope, which is in turn, with the A and the B probe wires, connected up to our toggle box. Let's go ahead and get a vertical view of see what's going on here. So here's A and B toggle, and here's ground. For this box, just like a breadboard, we see that everything vertically here, well, at least for a horizontal of a breadboard, everything vertically here is connected as a single circuit. Same thing for this column and this column. So if we actually look at what we're attached to, we go from off to curve tracer in order to get curve tracer readings. Note that the differential measurements from A and B are what we're going to be measuring from for this curve tracer experiment. Alrighty folks, let's go ahead and take a look at how we use the CV machine. Now if we take a look at this thing, it seems like a big jumble, but let's just make sure a couple of basic things are done first. First of all, this switch right here, we want to make sure is in the off setting. And we want to make sure that this knob here, which controls the variable supply to the actual sample, is turned all the way counterclockwise. Now, inside this, you'll never really have to mess with things. But we have our differential probe wires and our ground probe wires attached to the right side terminals. All that means is that when we use this switch later, we're going to set it to right, not off. Okay, so let's go ahead and turn it on. Here's our power switch. Light comes on here. And let's zoom out and take a look. Alright, so nothing's really happening at first until we adjust the intensity of our scintillating CRT screen. Now, we can damage the screen if we're not careful, so let's make sure that this is just bright enough to see, but not so bright that we damage anything. A general rule of thumb is this brightness is pretty good. Now, again with this thing, this can also damage your sample, so make sure that it's always in a controlled region, and you know exactly what it's set to. So, let's go ahead and turn it up for use in a measurement. Note that since we don't have anything hooked up, we're going to see our open circuit. Now, if that's a little bit confusing, just remember for an IV curve machine, I stands straight up. So that's your vertical axis, and V is your horizontal axis. This is open circuit, so for no matter how much voltage we pass, we get no current. Let's go ahead and see what happens when we add a resistor. Alright, so we have our resistor loaded up. First thing we're going to do is set this to right. Alright, so let's go ahead and take a look at the curve. Nice, we got a nice diagonal line, and using these knobs here on the right, we have the vertical adjustment knob to change scales, and we have the horizontal knob to change scales. So this seems pretty nominal for a resistor. No, we get this diagonal line. That's exactly what Ohm's law tells us we should get. Let's load up a capacitor and see what happens. Okay, so here's our capacitor. Remember that what's happening is we're sweeping a current signal back and forth across our device. So what we should actually expect to see is something that resembles somewhat of an AC signal. Now, if we recall for a capacitor, when it's in use, the current and the voltage should be 90 degrees out of phase with each other, which is why we see this kind of oval pattern here. Generally speaking, anything that's rather loop-shaped indicates that you have a capacitance somewhere in your circuit. Let's go ahead and load in a diode and see what happens next. Here's what happens when we have a diode inside. Note that we have relatively little current passing for negative voltages, and as soon as we go to a positive voltage that goes beyond the activation voltage, we get this knee in current where it suddenly shoots up. Generally speaking, these very sudden shifts in exponential growth represent something like a diode in your circuit. Alright, once you've made sure that you got the curves that you're looking for, first thing we're going to want to do is to remember, turn down the intensity and turn down your controllable voltage supply. Turn off the machine and restore this knob back to its off position, which is vertical. I know it doesn't look like that, but it's vertical. Alright, now we can go back to our toggle box, go from curve tracer setting to IV to start taking measurements.
So coming over to the IV machine, we're going to want to make sure the GPIB is plugged into the IV machine. Then we will turn it on. That is all we will be doing on the actual IV machine. So coming over to the computer to actually control the IV machine, make sure you plug in your flash drive so you can get data later. And then click on Semiconductor VI Launcher. You're going to want to click on Current Meter DC Voltage Source. Now this is the actual display where you'll be getting your curves. You can control your voltage scale here. I'm going to put it at negative 2.5 to start and have it scale through to 2.5 volts. Remember, you can change these settings, but you do not want to overwhelm your device with high voltage. So in general, I would stay below 5 volts. Here, we will change our voltage step. I'm going to put it at 0.05 volts, just so it doesn't take an incredible amount of time to get your data. Now, I have an ohmic resistor loaded, so we'll just start measurement and see if we get the curve we expect. It actively loads the data points it's collecting on screen. You can see your voltage scale changing and your current scale changing as it goes. Right now, we are getting the expected ohmic curve for a resistor. This is a linear curve between voltage and current because V equals IR. Now, once the curve is finished, which will be here in a second, if the data looks good, or if you want to report it later, it's a good idea to just save it in general. Click on Export Collected Data. Navigate to your flash drive and save it. It should be of the correct file type already. So here we've measured out the IV trace of a capacitor. As we expect from a capacitor, when you change the voltage, you shouldn't expect much change in the current. This current scale is quite low, and this curve looks fairly noisy. This is as expected. At higher voltages, we get a slight amount of current. This is somewhat expected because no capacitor is going to be ideal. Here we have taken a trace of the diode. Now, for the diode, we set our voltage from negative 1.5, because we don't want to push it to breakdown, to 0.8, because we know that a perfect diode would start to act as exponential current with voltage after about 0.6 to 0.7 volts. Here we can see that where it starts to shoot off to higher current regions right at about 0.6 volts. This is an expected Shockley curve that you've learned about. So now to remove your sample, remember to lift up your probes. The reason for lifting up these probes is you do not want to scratch your device when you remove it. Now, in general, for troubleshooting, you do not want to have pressed your probes too far into your device. This can scratch through a contact or an oxide, and if you have a bad trace on your curve tracer or your IV curve, it likely could be that, and it's worth checking. If you have scratched through a contact, there isn't really much you can do besides move to a different contact and remeasure, so hopefully you'll have another contact. But just as a rule of thumb, don't move your probes too far into the device, and always make sure you know where you're at. Now, as far as most of your devices will be minorly light sensitive, so when turning on your microscope light, I would leave it at a low level, and in general, turn it off when you're not looking through it.
Frequently, we find it convenient to take multiple measurements from a single curve set or single probe setup. The way we can do that is by switching which curves we consider the differential measurements. We can just do that by saying, I want to measure, instead of measuring from A to B, measure from A to ground. We can move the ground in that case to the second contact, which actually brings up our next point of troubleshooting. Frequently, when we play around with these little probes here, what can happen is these little knobs get really loose. If you want to fix something like that, the easy way to take care of something like that is make sure these are actually screwed in here, is we can just lift off the top of the toggle box. And each of these can be tightened with just a couple of turns of your fingers. That's really all it takes, and it's polite for the next person who uses the machine to make sure that those are screwed in all the way. You just put the back on just like this. Make sure that we're nice and closed, and voila! When working with the CV machine, always remember that when you actually intend to take data, make sure that the switch here is turned to right when these wires are plugged into the right side of this device. That way you can get measurements. When working with a LabVIEW virtual instrument, it's important to remember that the machine won't actually run until you've run the virtual instrument. The way that happens is you'll first diagnose it when you try to click on things, and things just kind of like underline or perhaps even try to move buttons like this. That's really inconvenient for us. What we have to do is start the machine. So to do that, we go to the top left portion of the screen, and we see this button here that says Start. We click on Start, and now our virtual instrument is in the operating mode.
Remember to turn off the IV machine. And you don't actually want to turn off the computer. It just seems to be better if left on. But if you do need to log in, the password is processing_lab. The PM processing is capitalized. You can just turn off the monitor and it's fine.